All right, so in this particular integral, when you have sines and cosines next to each other, you don't always have to have both the sine and the cosine to use these rules or cases that I'm going to give you. And they're similar, these are similar, just a different wording of the ones on the notes that I gave you. So case 1, what we can have happen here is we can have the sine power be odd. The sine is odd power. Okay, I'm referring to the powers when we talk about odds and evens here. If we have case 1 where the sine power is odd, what you need to do to help you evaluate this integral is use the trig identity sine squared x equals 1 minus cosine squared x. Okay, these things that I'm giving you aren't like how to work the integral out step by step, but it's how to make it into something that you could use substitution on, or something that you might just know the integrals, you can distribute. So there's a lot of techniques that we can use, but this is just a technique to get started being able to work this out. So case number 2, the sine power is even, the sine is even, and the cosine is odd. So in case 1, the sine is odd. I guess it really doesn't matter what the cosine is, or even if you have a cosine power. Okay. So in this case, case 2, if the sine is even and the cosine is odd, what you're going to use is you're going to use the cosine squared of x equals 1 minus sine squared of x to replace one or more of the cosine squareds. And then utilize, see what happens there. I think the directions that I gave you actually might give you a little more detail. So the third case, the third scenario here is that both are even, both or 1 are even. And you can say both are even because if there's no power of sine, it means it's actually even. So this would even refer to like if you just have cosine squared or just sine squared or sine to the 4th. So case 3, you're either going to use sine squared x equals 1 minus cosine of 2x over 2, and or cosine squared of x equals 1 plus cosine of 2x all over 2. And all of these are just trig identities. That's all they are. Yep. Okay, so what we're going to look at are we're just going to look at some examples of just this now. I could give more notes like over the secant ones, but we're just going to look at maybe 2 examples here of, go ahead. 2x, cosine 2x. If you look at the identities, you'll see that it's cosine 2x. Okay, and sometimes none of these actually work. Sometimes you just have something where you can just use normal substitution too. So sometimes you'll make, by just trying one of these right away, you're just going to make it a more complicated problem. So let's just take a look at...
real quick,
yeah.
The very bottom there, is that a minus? Is cosine squared x minus or equal? Is that okay, equal?
If you just look at your trig identities, you can see that what they are. These are the... All right, so let's just take a look at the integral of... We're just going to start off with one. The integral of sine to the 5th power of 2x cosine of 2x dx. Okay, and this one's kind of a little review here. In fact, this is a case where none of these actually are necessary. Typically, if one of the trig functions has a power on it and the other one doesn't, you can just use basic U substitution. So these are ones that we had back in Calc 1. So if you have an integral that one of them has a power on it and the other trig function doesn't, like this is with sines and cosines, you can just let U equal the trig function that has the power, but not the power. Because why is that going to work? Because what's the derivative of sine? Cosine. So this will become a u to the fifth, and this will become part of your du. So, don't just jump and start using these right away. Sometimes regular substitution works. But these are just guidelines so that if substitution doesn't work, you have a way to go. So basically your first line of defense is always, hey, can I just use some regular substitution here? Could I just use a trig identity to change this around a little bit? Or maybe do I just know these antiderivatives? Because remember that you've got that list of integrals that you know, and I just gave you another one. Some of those trig integrals that you know actually are things like our secant tangent. So you have integrals that you know that involve secant times tangent, or cosecant and cotangent, or secant squared. So there are some powers of trig integrals and things that you already know, so utilize this too. Don't just say this is the only way. We're just adding some more methods for more complicated problems. So I'm going to let u equal the sine of 2x here. And so my du is going to be the cosine of 2x times what? 2 dx. So this integral will become u to the fifth. And what am I going to replace that with? 1/2 du. So now my integral is actually pretty easy. I can just use the power rule. And if I add 1 to the exponent and divide by the new exponent, there's my antiderivative. Put my u back in. So I'll have sine to the 6th power of 2x. And I can put a 1/12 in front of it, or write the whole thing over 12 and then plus c. And that is my whole antiderivative. All right, so now let's take a look at another one. Let's say now this time, example number 2. I want to take a look at the integral of sine to the 5th of x cosine squared of x. Now that looks like a really similar problem, doesn't it? Kind of. Okay, but what makes it not so? Why can't we just use regular substitution now? Because they both have powers. Okay, and that's okay that they're different powers, but the fact that both of these have powers, now that's okay with like secants and tangents, because what's the derivative of tangent? Secant squared. So if you've got a tangent and a secant squared, that'll work out good, but here it doesn't. So this is where I'm going to use the guidelines. So what do the guidelines tell us? If is there one for odd power of sine, even cosine? Yes. Or sine odd? This would be case 1, right? So what does it tell us to do to start with? Use sine squared x equals 1 minus cosine squared x. So here's how we are going to do that. So I have sine to the 5th. Okay, sine to the 5th. So, and any sine squared can be replaced with 1 minus cosine squared. So sine to the 5th is how many of these? 2.5. So basically I can take this sine to the 5th, and in place of sine to the 4th of x, I can put 1 minus cosine squared of x to what power? Squared. And then I have an extra sine of x and a cosine of x. Now what I've actually, cosine squared, thank you. Okay. Okay, so now notice what I've done. The change of events. Haven't I made it so only one of the trig functions has powers? What trig function has the powers? Cosine. And which one doesn't? Sine. So can I use substitution now? So let u equal? No. Just cosine of x, and du is negative sine of x dx. Okay, so my integral is going to become the integral of 1 minus u squared squared. And then this part is going to become another what? Cosine squared becomes what? U squared. And what am I going to replace the sine x dx with? A negative, not just a negative du. Okay, now does this integral look impossible now? No, what can you do? Foil. Foil that and distribute the negative u squared, and then you can just use the power rule. So if I FOIL that and distribute u to the negative 2, if I FOIL that, I'm going to get 1 minus 2u squared plus u to the 4th. That's what I get if I FOIL that. If I then distribute the negative u squared, I'm integrating, let's see, negative u squared, and then negative u squared times negative 2u squared is positive 2u to the 4th. And then negative u squared times u to the 4th is minus u to the 6th, du. And now the power rule. If I add 1 to each of the exponents, add 1 to the power, divide by the new power, I'll get negative 1/3. Can I just put the u's in now? Is that okay? Yeah. What's my u? Cosine. So this will be cosine cubed of x. Add 1 to this power, that'll be cosine to the 5th of x. Yep, and then we'll have a 2/5 in front. And then this one, if I add 1, it'll become cosine to the 7th of x. And divide, that'll be minus 1/7 plus c. Okay, so next example we'll look at, let's say I would like to evaluate the integral of sine to the 4th power of 2 theta d theta. What are we going to use here? Case 1, 2, or 3? 3. I would use 3. And since I've only got sines, I'm going to use the identity sine squared of x equals 1 minus the cosine of 2x over 2. Now, what is the difference between this identity that I'm using and my problem? What is my x? My x is 2 theta. Does that make sense? So this is like this. So basically this is saying sine squared of 2 theta is equal to 1 minus the cosine of 2 times 2 theta, or 4 theta over 2. So I have to make that translation between what I have as my x. All right, so this is actually this squared. Would you agree? What we have in our integral is actually squaring that identity. Yes? Do you see that? Okay. So my integral is actually going to become this quantity, 1 minus the cosine of 4 theta all over 2 squared d theta. So what can I use now to work this out? What can I do to this integral? Square the top and bottom. How about we square the top and bottom? So I'm just going to use FOIL on the top. And if I square the bottom, what number can I pull out in front of my integral? So I'm going to pull out a 1/4. And then I'm going to FOIL that. So 1 times 1 is 1. Minus 2 cosines of 4 theta. And then plus cosine squared of 4 theta d theta. Okay, we got more to do here. What I want to do when I look at this now is I want to say, okay, could I work that integral out right there? Do I know the antiderivative of 1? And the antiderivative of 2 cosine of 4 theta, could I find that? U would be 4 theta. You just have to divide by 1/4, or divide by 4, multiply by 1/4. Now this one, do I know the integral of cosine squared? No. Now I'm going to use this, a different identity. I'm going to use the identity the cosine squared of x equals 1 plus the cosine of 2x all over 2. And in this case, what's my x?